we get started, let's go ahead and review over chapter 17. We'll get to your homework in just a moment, but tomorrow we got a quiz over chapter 17. Didn't want to give that to you coming off a 3-day weekend, so wait until tomorrow for that quiz. Chapter 17, all about sound. Remember we said sound is a longitudinal, three-dimensional wave that travels through then any elastic medium. The more elastic the medium, the faster sound will travel, right? And so there's 3 factors that affect the speed of sound. What are those, Audrey?
Temperature, hardness, density.
Temperature, hardness, density. 2 of those are positive factors. Temperature and hardness, and obviously that means density is the negative factor. We said that through air, sound will travel at different speeds depending on temperature. That's true for any medium, but air is most noticeable, and that's usually where we're hearing sound anyway. What's that equation for the speed of sound in air, Audrey?
31.5 times V sub air. Yeah. V sub air. No.
V sub air equals 331.5. That's the speed of sound at 0 degrees Celsius. And then we've got to account for the temperature.
Tc plus M273 and divided by 273.
There we go. Change the Celsius to Kelvin so we get absolute temperature. We don't have to worry about negatives anymore. Divide by 273 to get that relative temperature. Take the square root times 331.5. There's our speed of sound in air. We used this for the Doppler effect. Remember that shift in wavelength and frequency due to either a moving source or a moving observer. What was that equation, Michael?
F sub O equals F sub S times the quantity of the V sub air plus V sub O over V sub air minus V sub S.
There we go. And of course, frequency is going to be measured, class, in hertz. Remember, if one object is approaching the other, if the observer is moving toward the source, it's positive. Moving away from the source, negative. If the source is moving toward the observer, positive. If it's moving away, it's negative. Of course, that would give you a back-to-back negative, which would give you a positive result. We talked about as an object moves faster and faster and faster, then the frequency gets compressed more and more and more until if the object actually travels at or above the speed of sound, what's produced, class? Shock wave, right? Now, speeds at or above the speed of sound are called supersonic or Mach speeds, but it'll produce shock waves. Kind of building on that idea of shock waves. Sonic boom is what we hear at ground level. There's a lot of energy, if you will, in a sound wave. And if we took the flow of energy per unit time, per unit area, or power per unit area, that's called intensity. The strength of a sound wave is called intensity. And so we did have this equation, which we won't use often, but power per unit area is intensity. It helps us remember the units for intensity, though. What are our units for intensity, either of you? Watts per meter squared. And we said that 2 factors affect the intensity of sound. Do you remember what those are?
Distance.
Well, that affects the intensity that's perceived. That's true, the distance from the sound. We're going to get to that in a minute. But an actual sound, an actual wave as it's produced, there's 2 things that affect the intensity.
No.
Amplitude and frequency. Remember, amplitude is just more air coming out, right? Projecting softer, projecting louder, that's amplitude. And then frequency, remember, is the pitch, right? A higher pitch is more hurting, damaging to the ears. It's cringeworthy, especially depending on who it is. Then the lower pitches, right? The lower frequencies have less intensity to them. So both frequency and amplitude affect intensity. Now, distance from the source also affects intensity, and that was one of the equations we used in our homework. What was that equation, Michael?
K. No.
There's not a K in it.
I don't know.
Audrey?
Beta.
Well, that's getting to the next thing we're going to talk about. I1 R1 squared equals I2 R2 squared. The distances from the source affect the intensities that are perceived. So at a closer distance, for instance, higher intensity. Further distance, lower intensity. But there's that squared relationship with that distance because it's a 3-dimensional wave, so it weakens more rapidly than just a 2-dimensional wave would. This is really random, but I was driving along the road the other day, had a water bottle, like this one, just sitting in the cup holder. And of course, as you drive, there's a little bit of vibration in the car because of the motor, seeing these little perfect circular ripples emanating out in the water bottle. It's like two-dimensional waves. Anyway, nerd moment. Okay, anyway, so distance from source. Now here's the thing though, we don't perceive intensity. Intensity is what actually exists. That's the actual strength of the sound wave. What do we perceive? How does the human ear perceive intensity, class? Loudness. Loudness isn't measured in watts per meter squared. Loudness is measured in decibels, right? Decibels. We had an equation to go from intensity to loudness. We use the beta to represent loudness, bells, decibels for loudness. And what was that equation? This is the other equation we needed for problem 15 in the homework. There we go. Beta equals 10 times the log of I over I sub 0. So we'll take the intensity, or I sub naught. We'll take the intensity of a sound, compare it to the, what do we call this I sub 0, this lowest intensity we can hear?
Threshold of hearing.
The threshold of hearing. Do you remember its value in watts per square meter? 1e-12 watts per square meter. And so we take whatever intensity we've got, compare it to 1e-12, that gives us our relative intensity. Take the log of that, that converts it to loudness, but it's in bells. Remember we said a decibel is the just noticeable difference from one loudness to the next, so multiply by 10 to go to decibels, and that gives us our loudness in decibels. So we needed this equation and this equation for the homework. We're going to get to that in just a moment. We also said that the human ear distinguishes different frequencies as pitch. So if loudness is the way the human ear perceives intensity, pitch is the way the human ear perceives frequencies. There's a range of frequencies we call the audible spectrum. And what is that group of frequencies that a healthy human ear can hear, Audrey?
20 hertz to 20,000.
Good, 20 hertz to 20,000 hertz. Anything lower than 20 hertz, any frequency lower than 20 hertz, the human ear can't pick it up, but the sound waves are still there. What do we call these really low frequencies below audible sound?
Subsonic.
Not subsonic. That would be speeds that are slower than speed of sound, which is like subsonic flight, which is what pretty much all flights are that you would have flown in your lifetime so far. Not sub, though sub does mean below. Ultra means above. Infra, there we go. So infrasonic. Infrasonic, sonic again meaning sound, and then infra meaning below. So infrasonic waves have frequencies lower than 20 hertz. Higher than 20,000 hertz, Michael, are the ultrasonic waves. Those are frequencies above 20,000 hertz. Now, can every human hear 20,000 hertz? No. But that's what the healthy human ear can hear. Again, I said as we get older, we lose that upper end of the frequency range. So we can't necessarily hear, for instance, I probably at this stage of my life, I probably can't hear over 16,000 hertz. As I get older, that'll diminish more and more. Again, the more you're exposed to loud sounds, the more the eardrum is stretched by lots of high intensity sound, the more you're going to lose that hearing. People who work around power tools a lot, now they lose the ability to hear, period. But you also lose those higher frequencies as you get older. Another topic with frequency that your homework dealt with was this difference between one frequency and another frequency that sounds the exact same but lower or higher. And we said that two matching frequencies that blend perfectly are called an octave. And mathematically, what's the relationship between the frequencies in an octave? They are double, times 2, right? Double, or if you're going down, that would be cutting in half. So either multiply or divide by 2 to go up or down octaves. Speaking of octaves, number 16, let's start there. Middle C on a piano is exactly 264 hertz. Middle C. All right, if you go up one octave to the next C, it actually asks for the next 3 higher octaves and 3 lower octaves. What is the next octave above middle C going to be, class? 528 hertz. Then the next C is actually what we call high C, not the drink. And the next high C would be 1,000. What'd you say?
56.
1,050. I thought I heard 1,076. I'm like, that ain't right. 1,056 hertz. And if you were to go one more C higher, we would be up to 2,112 hertz. All right, questions on the higher 3 octaves? Audrey, make sense now?
Yeah, I just didn't think about it. And
Really easy math, right? All right, so Audrey, I'm going to have you take the next ones. Going down to the next C, which is where the basses like to sing, right around there. 132 hertz. Drop down another octave. We're at what we call low C, which most basses can't hit. I certainly cannot, but it's about 3 or 4 steps lower than where I would usually be able to hit.
66.
Just 66 hertz. And if you go down one more C, you're almost at the bottom of the piano. And you know the first note is an A. There's only 2 notes lower than this, though. So this is the almost lowest note on the piano.
33 hertz.
33 hertz, and it's just as well because by the time you're getting down here, you're getting down to the very bottom of the range anyway, where if you've ever played those bottom few notes, you really can't tell the frequency difference very well anymore anyway. Now, higher, of course, we have plenty of room to go higher, right? You could go one more octave, and I believe it takes you to the very end of the piano, right? 4 octaves above middle C is the end of the piano. What would the highest frequency be on the piano? This wasn't part of the homework, just asking.
4,224.
4,224 hertz. And we've got plenty of range above that, right? We could hear a few, but still another 2 octaves higher than that, right? The piano just doesn't go that high because, you know, ears. All right, questions on this? And usually that last note of the piano is not a great tune anyway. Just sounds weird when you hit it. Anyway, maybe it's just my piano or all pianos I've ever played. All right, questions on number 16. Octaves should not be a challenge for us, correct? Just double or half. All right, now, problem 15 was a lot more involved. Go ahead and read problem 15 from the homework if you would, Michael.
At a distance of 130 meters, a jet plane has a loudness of 130 decibels. What is the loudness when the plane flies overhead at an altitude of 2 times 10 to the 3rd meters?
All right, so we've got the airplane taking off, and it's, you know, you're driving in your convertible through Atlanta. Well, I say you're driving. You know how it is in Atlanta. You're sitting there and just stuck in traffic, and the plane is taking off right above your head because the runways go right over the freeway. It's great. And so it's really, really loud. Well, what if it were flying at an altitude, it says, of 2E3 meters or 2,000 meters? That's not usually where the planes will fly, but, you know, it's on its way up, okay? So it's been up in the air for a little bit now. Here's the problem. Distances from the source of sound affect class intensity, but it's asking about loudness. You can't substitute loudness for intensity because they're not one-to-one. Remember, loudness does not grow linearly. Loudness grows logarithmically, right? Not longitudinally, logarithmically, right? Loudness increases logarithmically. So before we can use this equation to show different distances, right? I know one of the distances is 130 meters. That's going to be squared. I know the other distance was 2,000 meters, 2E3 meters. That's going to be squared. But I don't know the intensity, right? It tells me a loudness of 130 decibels. The problem is I need to know what is that intensity. So I needed to first of all get this I by itself, solve for the I. Well, how do I solve for this I, class? 3 steps. First, divide the 10. Anti-log, right, 10 to the power, but if you just do second function log on your calculator, you've got it. And then finally, multiply the 1e negative 12. So you've done it already. I'm going to go and do that here. Divide the 10, take the anti-log, and multiply by 1e negative 12, and take it out of scientific notation. What is the intensity of 130 decibels? 10 watts per meter squared. Now remember, what's the threshold of pain? 1 watt per square meter. This is 10 times as intense. All right, so this is very high intensity. This is causing pain for sure to your ears as it roars over. It's like, you know, babies are crying, that kind of thing. Well, what about 2,000 meters? Is it going to be nearly as bad? Well, let's go and find out. So what you should have done then was take the 10 times the 130 squared, divide out the 2,000 squared, and you get a much lower intensity. What do we get for that second intensity? The intensity, this isn't the final answer, but the intensity at 2,000 meters. But it didn't ask for the intensity at 2,000 meters. It says, what is the loudness when it's reached this altitude? Well, That means I want to know beta. And I know the intensity. How do I get beta, class?
You divide by 1 and then 12.
Then take the,
Log.
and then
Multiply.
multiply by 10. So we divide by the 1e negative 12. We take the log. We multiply by 10. And we get, that's still pretty loud, but at least it's not to the point of pain. How loud is it at 2,000 meters?
106.
Was it 2 or 3 sig figs in the problem? Oh, it's only 2. Okay, so we're going to have to round to about 110 decibels. Did we get that for our answer on number 15? Did not. Does it make sense now? We remember it now. Again, coming off a 3-day weekend, not always super easy. All right, got a handout for you to help you review. We reviewed the terms already. Math is most easily reviewed by doing this. Little extra practice. I got a handout for you. Obviously, if you're watching on YouTube, it is in the description of the video. I want you to take just a moment and do the first box, finding the speed of sound in air. At different temperatures. I erased her too. There we go. Did I just run over something? I heard a crunch. Michael's like, it was my foot. Just kidding. Michael got the first box. Audrey got the first box. All right, 15 degrees Celsius, really straightforward. You plug in the 15, you add the 273, the 273, take the square root, multiply by 331.5, 2 sig figs. What are we rounding to, Audrey?
340.
Rounds to 340 meters per second. Is that what we got? For the second one, it takes a little bit more because the temperature it gives us is 86 degrees Fahrenheit. So we first have to change Fahrenheit to Celsius. How do we change Fahrenheit to Celsius, Michael?
You 5 nines, and then times the quantity of that one.
Good. Subtract the 32, take 5 ninths. Once you got that, which I believe is, you put it all in the calculator. Either of you right. I think it was 25. Plug that into the equation. We end up getting what for the speed of sound in air? Again, 2 sig figs.
I have 350 meters.
Around to 350 meters per second. 350 meters. Correction, that would be 30 degrees Celsius. Comes to 350 meters per second when you round. 349, it rounds up. All right, do we get both of those correct? All right, any questions on temperature in air, or speed of sound in air? All right, got a couple of Doppler effect problems. Go and read do the first one, the boat in the harbor problem. The boat in the harbor. The whistle means it's about to start moving, so it's not moving yet. It says it's 25 degrees Celsius. Do we remember what the temperature is, the V sub air is going to be for 25 degrees Celsius, class?
346.
Good, 346.346, or you could just use 346, honestly. It's not going to make a huge difference there. The V sub O, what's the observer's speed or velocity, class?
14.
Positive or negative 14? He's driving toward the harbor, so that's a positive 14 that gets added. What about the velocity of the source?
0.
0. The boat is sounding its whistle, meaning it's about to start going, but it's not moving yet, so we're going to assume no velocity. Also didn't give you one. So minus 0, don't even bother. Multiply by that by the 530 hertz actual frequency of the source. What about the frequency that is heard? Audrey?
551 hertz.
551 hertz. Good to go on that next one. All right, for the next one, policeman involved in a high-speed chase. Now, he's not chasing you, and we know that because part B says he passes you. Okay, so you should have pulled out of his way, but he's not got time to worry about you. First, this one car flies past you, and then next guy flies past you. That's the deal here. We're assuming, now in Georgia, we would say a cold winter day is 0 degrees Celsius. Depending on where you are in the world, you might be like, hey, 0 degrees Celsius, man, that's not a cold winter day, but whatever. All right, third box, at your seats. Two parts. He's driving up behind you, and then he passes you. All right, driving up behind you, the frequency of the source is the 555 hertz. He's driving up behind you. You're the observer. Are you going toward or away from the police officer? Away, because he's coming up behind you. So your velocity, the observer's velocity, is negative 36 in the first part of the problem. Wait, he's going 36, sorry. You're going 24. You're negative 24. You're the observer. The source is the police car. Is he going toward or away from you if he comes up behind you? Toward, and his velocity is
36.
positive 36. So we're going to add a negative 24. We're going to subtract a positive 36. The net result is subtraction in both instances from the 331.5. What do we get for the frequency you hear as he's coming up behind you? Michael?
667.
Ooh, that is not what I got. Audrey?
578.
I got 578. I think you might have put in a positive 24 up here, would be my guess. It sounded like you treated it like we were both going toward each other, but since he's coming behind.
Yeah, I had the answer written down, but I thought I did it wrong, sorry.
Oh, okay, yeah, 578 is correct here. Okay, so again, that's the 331.5 plus a negative 24 over a 331.5 minus a positive 36. Now that's the first instance. 578 is what you hear as he's coming up behind you. Then he flies past you. Are you going toward or away from him now? You're going toward, so your velocity becomes positive. Is he going toward or away from you? Away. So his velocity becomes negative, but we have a minus negative, which is the net result of a positive. And Michael, what did you get for the frequency you hear after he passes you?
537.
537 hertz. Audrey, did you have that one correct? All right, questions on that Doppler effect problem? Feel like we're good to go with Doppler effect for tomorrow's quiz. All right. Let's practice with loudness and intensity then. Next box on the bottom row. Finding loudness given an intensity, finding intensity given loudness. right, if a sound has an intensity of 3.40 negative 6 watts per square meter, rounded to 2 sig figs, what is the loudness? Audrey?
240 decibels.
No. Michael?
65.
65 decibels. So remember to find loudness. We're going to start by plugging the intensity in here, which is the 3.4 E negative 6. I'm maybe wondering if you've missed the negative. I wonder if you missed the negative 6. Anyway, we'll divide that by the 1 E negative 12. We'll take the log. We'll multiply by 10. And do you have it now? I'm really curious about this now. I'm going to try without the negative and see if I'm right, just because I'm curious about things like this. That's only 185 if you forgot the negative. Maybe you were really dyslexic, you did 4.36. I don't know. Anyway, got it now? All right, and then find the intensity of a sound that's 83 decibels. So if I know the loudness is 83 decibels, the intensity, Audrey?
2.0 E negative 4.
Watts per meter squared. 2.0 E negative 4 watts per square meter. Michael, did you have that correct? You did not. All right, so remember here, you're going to start with the 83 on this side for the beta, divide out the 10, take the anti-log times 1 E negative 12. I should get 0.000199. All right, which rounded to 2 sig figs is 0.00020 or 2.0 E negative 4 watts per square meters. Questions on that one?
I forgot what the anti-log is for my calculator.
Should be second function of the log button. Do you not have a log button?
I did, but I couldn't figure out how.
Oh, yeah, it's just second function. So, okay. So on your calculator, go ahead and start working on the next problem while I work with Michael. So 83 divided by 10. 8.3 negative to the anti-log of the answer. So second function log in answer, and then times, I don't know why I just did that. 1, so like 1 E, where's your E?
It's this, the negative 112.
Okay. And there's the answer.
Okay.
All right. You'll get a chance to practice that in the next problem as well. We've got a Blue Angels plane. They're flying at 350 meters, which isn't very high, and they're pretty loud. But if they were to go just 35 meters above their spectators, how loud would that be? I think I'm being very conservative on these loudness numbers. I'm pretty sure it's louder than this. But, you know. Because when they roar overhead, it is physically painful. All right, for sake of time, we've got 90 decibels at 350 meters. That's no good. I can't use loudness at a distance, class. I've got to change the 90 decibels into intensity, watts per square meter. So we're going to plug the 90 in here, Michael, and this is where we went through that same process. We're going to take the 90 divided by 10, which is 9, take the anti-log times the 1 E negative 12, and we get 0.001 watts per square meter. That's at 350 meters, that gets squared. That's the I1 R1 squared. Then we're finding I2 at 35 meters, and that gets squared. And we get intensity 2 is 0.1 watts per square meter. That goes in here to find the loudness now of the 0.1 watt per square meter. And so we'll divide by the 1 E negative 12, take the log, multiply by 10, and we get how many decibels for our answer? Anyone? 110 decibels. That actually came out evenly. 110 decibels should have been our answer for this. Again, I think it's a little conservative. I'm pretty sure it's louder than that. Questions on how to use these two together to find different loudnesses at different distances. All right, your homework. homework for this evening. Obviously, study over what you need to for the quiz. Okay, do whatever preparation is necessary to be ready for quiz over chapter 17. In addition, as we start chapter 18 in our next lesson, I need you to read over pages 266 to 271. You're going to see a lot of names. We haven't done a lot of names in this class. We're going to have a lot of names in this section. Page 276, answer questions 1, 2, 4 through 8. Questions 1, 2, and 4 through 8. Basically 1 through 8, but I'm going to let you skip number 3. Kind of a weirdly phrased question. All right. Have a wonderful rest of your day, and you are dismissed.